Hi friends, welcome back to our video series on energy and environment. The technologies in blast furnace energy efficiency will be covered today. We all have seen in a blast furnace, the iron oxides are reduced and the resulting iron is melted. That is the reason why blast furnace becomes the main steel melting section of all the integrated steel plants all over the world. So blast furnace forms a very, very important component for any integrated steel plant all over the world, because the efficiency with which you manage the blast furnace depends on the efficiency of the entire plant. So much of energy in terms of quantity and quality that is going into the blast furnace makes the entire integrated steel plant energy efficient. That is exactly what we need to understand. So approximately 70% of the global steel production involves the use of blast furnaces. The sizes of the blast furnaces installed over a very wide spectrum ranging from less than 100 meter cube to more than 5,000 meter cube. Larger blast furnaces have less heat losses and enable installation of heat recovery equipment more cost effectively. So let's see the block diagram, or rather schematic diagram of the blast furnace with the source of Wikipedia. We have seen the first one is the iron ore plus calcareous sintering. That's in. So second one is the coke that is coming here. And then third one is the conveyor belt. This is the conveyor belt. It's coming all through the here. It's coming to the fourth. Fourth is the feeding opening into this. Then 5 is the layer of coke. This is the layer of coke. And then 6 is the layers of sinter and iron oxide pellets. That's what we normally call it as ore. Okay, that's the combination. This is how it is arranged here. As it goes on, you can see it goes in layers. Then 7 here, what we call it as a hot air tires, we normally call them, where the temperature is around 1200 degrees centigrade. Then number 8 here is the slag that comes, the slag after the molten metal, whatever is the leftover in forms of slag comes over. That's what we normally call it as a 8. Then 9 here is the liquid pig iron that comes out from the right side of this. And then left slag, whichever is the floating on the liquid molten metal comes out through this. And the liquid metal that is the bottom comes out. That's the 9. So 10 are the mixers, basically to remove that slag. We have the mixers. And 11 is how we are tapping this is the tap for pig iron. From this pig iron goes for the continuous casting machine. Then 12 are the cyclones, basically for removing the dusts that are coming from here. 12 are the dust cyclones, basically to remove the dust. Then 13, these two are the air heaters. Okay, and this air heaters, number 14 is the smoke outlet chimney. So we have the checkers here. Basically, these two are called as the blast furnace coke oven, coke oven gas making heaters, air heaters. And when you heat this heater to height up to 1200 degrees centigrade, this is sent through the tires into the blast furnace. And from this, we have the 14 is the smoke outlet and 15 is air feed for air heaters. Then we have the 16, which again another conveyor, mainly for coming this 17, 18, and 19. So this is basically forms the entire blast furnace that we have. And then from this, we have seen the cold blast blowers and hot blast ovens. These two are the hot blast ovens. Hot blast means hot air when it is sent at high pressure. We normally call it as hot blast ovens, are other important elements of the blast furnace system. While the former provides the necessary airflow, that is the blast blowers provide necessary airflow at 3 to 5 bar pressure, the hot blast ovens increases the temperature of air to 900 to 1350 degrees centigrade. Ore, which is normally ferrous oxide or ferric oxide, sinter or pellets, coke and lime, basically lime that removes impurities and acts as a flux, are added to the blast furnace from the top, which we are taking it as a hot blast, where the hot blast, which is nothing but the heated compressed air, is introduced from the tires at the lower part. So hot air, hot blast is going from here and the ore is coming from this. So auxiliary reductants, we normally call them as fuels like coal, fuel oil, natural gas, or other alternative sources can also be injected from the bottom of the furnace. At lower parts of the furnace, coke is gasified and the resulting carbon monoxide reduces the iron oxides as it ascends the furnace from bottom, as it ascends in the furnace. The molten iron trickles down and collects at the bottom. The impurities that are removed by the air with the aid of calcium oxide from the slag that floats on the molten iron. This is the slag that floats on the molten iron. The hot gases leaving the blast furnace still maintain a pressure of 2 to 3 bar. In addition, a gas with low calorific value like 3 million megajoules per Newton meter cube is produced at a rate of 1300 to 2200 Newton meter cube per ton of pig iron. So after cleaning, this gas can be used as a fuel anywhere in the process plant. The practical minimum energy used for a blast furnace is 10.4 gigajoules per ton of liquid metal. However, based on information obtained from 6 efficient hot blast stoves and blast stoves around the world, the average primary energy requirement for a blast furnace system is reported to be 1.8 gigajoules per ton of hot metal for the hot blast stoves and 11.6 gigajoules per ton of hot metal for the blast furnace itself. Now, there are very few alternatives to this blast furnace in the integrated steel plants, that is direct reduced iron and smelting reduction technologies offer an alternative to blast furnaces for iron production and are gaining importance day by day. Now, with this background, let us see some of the technologies, blast furnace system technologies and measures that have been practiced all over the world in order to improve the energy efficiency of the blast furnace. So we'll be seeing basically the technology, that is the measure, then the energy saving potential of each measure, and what are the carbon dioxide emission reduction potential of these things. So first one, if you see the use of high quality ore, if you use this measure, then the use of high quality ore increases productivity and energy efficiency of iron making process. This technique will reduce the carbon dioxide emissions by 15 to 80 kg per ton of hot metal. The economic benefits are connected with increasing productivity and reduced energy consumption and decrease in the demand of reducing agents. That's the first measure that we will be considering. The next, number 2, is the measure is the pulverized coal injection. For every ton of coal injected, 0.85 to 0.95 ton of coke production can be avoided. Energy savings are estimated to be 3.7 gigajoules per ton of injected coke. The average pulverized coal injection rate at global level is considered to be 180 kg per ton of hot metal. And if you see global level, there is a reduction of 10 million tons of carbon dioxide that could be saved every year using this particular thing. The cost savings range from different things, basically 3,000 to 4,000 rupees per ton of hot metal can be expected, and lowering the hot metal production cost by approximately 4.6%. Okay, so investment of coal grinding equipment is also essential for we need to consider whenever we are taking this measure, that is the pulverized coal injection. So the next measure is the top pressure recovery turbines. That's the latest technology. With this, using this 40 to 60 kilowatt hours of electricity can be produced per ton of hot metal. A dry process top pressure recovery turbine installed at 1 million tons per year of blast furnace produced 55.4 gigawatt of electricity per year. And that is the shown by the literature. So if this TRT were installed worldwide at all the furnaces working at elevated pressure, carbon dioxide emissions at the rate of 10 million tons per year could be reduced. That's the effect of this top pressure recovery turbine measure. Then the next innovative measure is increased blast furnace top pressure, that is greater than 0.5 bar gauge pressure effect. Increasing the blast furnace top pressure. This technology reduces coke rate and tire level injectants. Furnaces operating at high pressures can produce electricity in the order of 0.35 gigajoules per ton of hot metal. The system has recovery turbines installed. And the effect is lower emissions due to reduced energy consumption, and that are all expected from this. So next measure is on improved hot stove process control. Energy savings typically range between 5 to 12% and may reach 17%. This may typically equate to 0.037 gigajoules per ton of hot metal. That's the energy savings that is expected. And emissions can be reduced by 22.6 kg of carbon dioxide per ton of hot metal by using this method. Then the next measure is blast furnace process control. By implementing this technology, coke consumption could be reduced to approximately 0.458 tons of coke per ton of hot metal. This was actually achieved in an Australian steel plant as per the literature. The emission reduction potential of the technology is 24.4 kg of carbon dioxide per ton of hot metal. So the next measure is heat recuperation from blast furnace stoves. This technology can reduce the energy demand by 0.24 gigajoules per ton of hot metal. Its global application has 0.2 joules per year energy reduction potential. With global application of this technology, carbon dioxide emissions could potentially be reduced by 20 million tons annually. Various systems allowing fuel savings between 80 to 85 megajoules per ton of hot metal have been installed. By recovering 40 to 50% of the sensible heat from the stove flue gases, 0.125 gigajoules per ton of pig iron saving has been realized in Japan integrated steel plant. Then the next measure is increased hot blast temperature that's greater than 1000 degrees centigrade, hot blast temperature. The total energy savings potential, possibly by a combination of techniques, is of the order of 0.5 gigajoules per ton of hot metal. And energy savings will result in reduced emissions. Then the next measure is on improved combustion in hot stoves. Energy savings can be around 0.04 gigajoules per ton of hot metal, and this can also result in reduced emission levels. The next measure is on injection of coke oven gas. The replacement rate of coke oven gas is about 1 ton of gas for 0.98 ton of coke. Since 2002, as a case study, a plant in Austria has operated their small blast furnaces with a simultaneous injection of reduction gas and heavy fuel oil as standard operational procedure, with the replacement of 70% of the heavy fuel oil by coke oven gas. In 2004, these furnaces averaged an oil injection rate of 45.5 kilojoules or kg per ton of hot metal and coke oven gas rate of 46.9 kg per ton of hot metal, with a total equivalent coke rate of 477.8 kg per ton of hot metal. That's the strength of the savings potential of injection of coke oven gas directly. And emission reductions due to replaced coke, instead of 1.98 ton of coke per ton of coke oven gas, and reduced flaring of coke oven gas will also result. That's the advantage of this measure. Then the next measure is on improved recovery of blast furnace gas. Although every blast furnace has a gas recovery system, but if we have improved recovery, then the energy savings of 35 megajoules per ton of hot metal to 66 megajoules per ton of hot metal are reported in the literature. And emission levels also can be reduced by 4 kg of carbon dioxide per ton of liquid hot metal. Then the next measure is on injection of oil. For every ton of oil used, this can reduce the coke demand by 1.2 tons. It's again a trade-off between injection of coke and the oil, because the carbon dioxide reductions will vary depending on the composition of the oil, and in particular the carbon and hydrogen contents of the oil. That's also the thing. Then the next measure is on using natural gas. Fuel savings are estimated to be 0.9 gigajoules per ton of hot metal, and the savings of 54.9 kg of carbon dioxide per ton of hot metal are estimated by the injection of 140 kg of natural gas per ton of hot metal. The next measure is on dry dedusting of blast furnace gas. Dedusting using dry methods. So dry dedusting will reduce water consumption by 7 to 9 meter cube per ton of hot metal. It may also increase the power generated by TRT system by 30% compared to a wet type dedusting. Like wet type dedusting is nothing but scrubbers, what happens. So indirect greenhouse gas reductions will arise due to increased power generation in the TRT if at all it is installed. Then the next measure is on plastic waste injection. The energetic value of the 0.4 million ton plastic used in Japanese steel plants yearly is equal to 20 petajoules. So for every ton of plastic waste used, coke use can be reduced by 750 kgs. That's the thing. So ultimately this will result, for every ton of plastics used, carbon dioxide emissions linked to the production of 750 kg of coke can be avoided. So the next measure is on Oxy Oil Injection. Up to 130 kg per ton of hot metal, Oxy Oil Injection is applied, and this can result in a savings of coke of about 15 kg per ton of hot metal. So the emission levels, you have a reduction in carbon dioxide emissions roughly at 50 kg of carbon dioxide per ton of hot metal. So the next measure is on charging carbon composite agglomerates. So on charging 30% of carbon composite agglomerates, coke rate and the total reducing agents rate are reduced by 30.2%. That's the advantage. And the emission level reduction in coke input rate may ultimately reduce the blast furnace emissions. Then the next one is top gas recycling blast furnace gas. A 26% coke saving per ton of hot metal from the current blast furnace coke consumption is very easily feasible by the application of the top gas recycling blast furnace technology. A 15% reduction of carbon dioxide per ton of heat recovery system is expected to be feasible without continuous casting system. Up to 50% carbon dioxide reduction is possible with this recycling of blast furnace gas from the top. Then the next measure is on slag heat recovery. The associated energy savings from the slag heat recovery is around approximately 0.35 gigajoules per ton of hot metal. And there will be a reduction in carbon dioxide emissions if the recovered heat is adequately utilized. And then we have blast furnace gas recycling. Energy saving potential is approximately 0.35 gigajoules per ton of hot metal. And again, the associated reduction in the carbon dioxide emissions because of the recovered heat is fully utilized. That's what it matters. Now that's all about the efficiency, energy efficiency aspects of blast furnaces. This video basically covered the latest technologies all over the world available in increasing the energy efficiency of the blast furnace. Hope it is useful to us. Thank you for watching.